So in 2017, the field of natural language processing was advancing quite rapidly. We'd moved on from having to do feature engineering for all of our models. Neural networks were becoming standard. But then the way we were making progress in our field was by doing neural network architecture engineering. And so don't worry about the details, but basically for every paper that was coming out, on page 1 or 2, you would have this figure 1 with this really complicated diagram of the neural network architecture you had invented for your problem for this paper, and that was how you made progress. So here's the state of the art in question answering on the left, for natural language inference in the middle, and for named entity recognition on the right. And so the details aren't important, but the thing I want you to know is that this was how you did research in NLP. All these models were different from each other. They're all trained on different data. Pretty much the only thing they had in common might have been the word embeddings. Those might have been the same across the different models. And so if you then go to October 2018, our group at Google, we released a single model, and this is just a single model. And with this one model, you can get state-of-the-art performance across tens of tasks with a minimal amount of task-specific changes. And so when I say in minutes, I mean both in terms of machine time, you can fine-tune these very quickly, and minimal amount of human time. So this is showing a diagram of different types of problems you might want to do. You might want to do classification with a single sentence or multiple sentences, or you might have a tagging problem or question answering problems. So these are all different types of outputs, but they can all be represented in a similar way. And so that's what I'm going to tell you about in the first part of my talk today, is what is this model, how is it trained, and how can you use it for your tests. So this is called Bert, Bidirectional Encoder Representations for Transformers. It got a fair amount of attention when it came out. It was written up in the New York Times on some academic benchmarks that are commonly computed on. This is the squad question answering data set. It actually scored quite a bit above human performance. I'm not claiming this generally. I think this is, but it was well above prior work on this data set. And the paper will actually be published in NACL 2019, so a conference in June. And then even though the paper isn't published yet, the archive version already has over 100 citations. And we open sourced all of the code and released pre-trained models. And they've been downloaded from GitHub over 10,000 times. So in order to tell you about how BERT works, I first need to give you a little bit of an overview of how transformers work. And in order to tell you how transformers work, I just want to give a quick highlight about attention, because that's sort of the key thing that underlies all of these. So here is an example. So we're sort of zooming in a sub-portion of the model, and we're doing a translation task. So let's say we're translating from English to French, and we're translating either the sentence, the animal didn't cross the street because it was too tired, or the animal didn't cross the street because it was too wide. And so in English, if you just look at this word it's the same in both sentences. But if you translate it to French, you're either going to translate it as il or elle, depending on what it refers to and what is the gender, in the grammatical gender in French. And so to solve this translation task effectively, you need to know what it refers to. And so this attention allows the representation for a word to be dependent on its context. And it can pay more or less attention to different parts of the context depending on what's important for the problem. And so here is a screenshot of what the model actually learned, zooming in on one piece of the attention distribution. And you can see that when the animal didn't cross the street because it was too tired, almost all of the attention is going to the word animal. And when it's tired, it refers to animal. Whereas when we had the animal didn't cross the street because it was too wide, it is mostly depending on street for its representation. Or here it refers to street, because streets can be wide, and that would be the reason. So now let me tell you a little bit about how attention is used in the transformer. This is not a complete tutorial. I've put some links in the speaker resources. There's some really good illustrated guides that kind of break it up step by step. But I'll give you a little piece here. So the first step is that for each word, so if I say the animal didn't cross the street because it was too tired, for each word we first look it up and then we look up its word embedding. So that's the first piece. But each of these word embeddings is completely context independent. So now let's focus on just the word it. I want the word it to now depend on the surrounding context. So what I'm going to do is I'm going to take this word embedding vector and I'm going to project it in 3 different ways, and I'll show you how these are used. So from the word embedding vector, I'm going to create 3 different vectors, a query, a key, and a value, that'll be used to create the contextual representation. So the query is basically, what am I looking for? What should I be attending to? And so the query for the word it is going to be compared against the key for all of the other words in the sentence, which kind of show how good am I a representation for people who might want to attend to me. So we take the dot product between the query for it and the key for each of the different words in the sentence, and we'd normalize. So then we'd get a distribution like, well, it should kind of depend on animal 70% and street 10% and it itself 20%. And then after we have these weights, we multiply that by the value portion of the vector, which is the actual representation that should be moved forward. And from that, we get a new representation. And so that's just done once. Now in practice, we're going to do this multiple times in parallel. So maybe this particular attention head is really good at looking for co-reference. There might be another one that focuses its modeling power more on syntax. There might be another one that really specializes in looking, what's to the left of me, and so on. So we'll do this in parallel, and they all have different matrices for projecting the queries, keys, and values, so they can specialize in different things. And then I've just shown you one layer. This will actually be stacked in a deep neural network. So whereas for this first layer, we took the embeddings as input, for the second layer, it would take the output of the first layer, and so on. So this is the architecture, and it was pioneered for machine translation. And one of the really nice things was that, so it had slightly better results than LSTMs and recurrent neural networks. But the nice thing is that it could be trained much faster on more data. And the reason for this is it's much more parallelizable. So if you look across the words within the layer, there's no dependencies on the sequence. So if I'm looking at street in an LSTM, I would have had, animal, affects, didn't, affects cross, and so on. And here, there's none of those connections. And so then in June of last year, a paper came out saying, well, how can we use the transformer architecture as a good pre-trained representation? And so this is one of the main precursors to Bert, was this paper on generative pre-training by OpenAI. And so what they did is they used the transformer architecture to do the task of predicting the next word. So on the left, I've only shown 3 words in the slide to save space, but imagine the full sentence is there. So the animal didn't cross the street because it was too tired. When I'm at the first start of the sentence, I need to predict the. When I'm at the, I then need to predict animal, and so on. So I'm repeatedly making this next word prediction task. And so this can be trained on lots and lots of, there's sort of freely available labeled data. You just need raw text, and raw text, you can see what is the next word. So it's really good for sort of semi-supervised learning. And the other good thing is that this next word prediction task, it forces you to learn a lot about language. So if I have to say, okay, the animal didn't cross the street because it was too, as a human that tired is plausible, whereas something like elephant or, fireflies are not. And you can make these distinctions on the basis of the grammar, on the basis of the topic. And so you have to have learned a fair amount of language to do well on this task. And so what they did is they pre-trained the model on this next word prediction task. And then they took that entire network and use that to initialize their network for whatever task they actually wanted to do. So they looked at classification tasks. And so you would start with the network that you use for this next word prediction task, and then you would fine tune on your data that you actually care about. So on the right, let's imagine I'm doing, is this sentence grammatical or not? Is it acceptable or not? So just on the last word, I would then predict this binary classification task. And I would train on my labeled data for this task, and I would use it to affect all of the previous parameters. But because this language modeling task had forced me to put a good representation of language, you could do really well on these supervised classification tasks with much less data. So this was great, and it was great for classification problems, but it didn't work that well for non-classification problems. And one way you can think about this is that if you're doing a task where you need to find a span or you need to tag things in context, then you might really need the information that comes later. You might, just looking to the left might not be sufficient. So for the classification task, it was fine. We just put it on the end and we could look backwards and that was everything. But for these other tasks, that's not okay. So if I have this question of how far is Jacksonville from Miami, and then I have this passage, at the time I get to the answer is 340 miles. But at the time I get to that answer, I haven't yet seen why it's the answer. The thing I need to know to make this determination is coming later, as north of Miami. And similarly, if you think about something like part of speech tagging, if I say mark which area you want to distress, that word mark is a verb. If I say, hey Mark, which area do you want to distress? Then mark is a noun. And so, but both of these is just the first word in the sentence. So you can't tell anything just looking at that single word. And so we have this issue that for a lot of natural language understanding tasks, you need this information from the future. And so one thing you might say is, okay, let's just look at it then. And so if we say, okay, let's just add some more arrows. You can, instead of only attending backwards, you can also attend forwards. So that's the picture on the right. If you do that, then actually the model can completely cheat and not learn anything. So if I have my task where at the start I need to predict the, and at the I need to predict animal, and so on for the animal didn't cross the street because it's too tired. So when I'm predicting the, I could actually, maybe I'll use the pointer if I can. So if I'm predicting the, if I'm allowed to attend to other things in the input, then I can just look backwards and I see, oh, it's the, I just need to copy. And similarly for animal, I could just copy the one to the right is animal, and so on. So the model would just learn to copy paste, and it wouldn't have to learn anything about language. So that's why the pre-training approaches in the past either only look to the left, or some of the models said, okay, I'm going to only look to the left, and then I'll train a second model where I only look to the right, and then I'll concatenate them at the end. But that still doesn't help you for these problems like Jacksonville is 340 miles in Miami, where you really want to see both sides simultaneously. And so this Bert model addressed this problem. How are we able to look backwards and forwards simultaneously without letting the model cheat? And so Bert is trained with two pre-training tasks, and I'll tell you about both of them. One is this fill in the blank task, and the other is this next sentence prediction task. So in the input for Bert, it gives you full passages, and then some percentage of the words are masked out. So you don't get to see them at the input layer at all. They're replaced by dummy tokens. And then now the model can freely attend across the entire input. So it's okay to have this transformer self-attention over everything because the cheating answer isn't there anymore. And so then the task is fill in these blanks. So given these pair of sentences, everywhere you see a mask, please predict which word goes in that blank. So that's one task, and this forces a really good representation of words, and it is able to combine information backwards and forwards. And then there's a second task called the, is this the next sentence? So this is to encourage the model to really make correlations across sentences, which is really good for tasks like question answering, where you don't want it to just separately analyze a question and separately analyze an answer, but you really want it to be linking up the connections between the question and the potential parts of the passage that give you the answer. And so for the Bert, the input is you give 2 sentences at a time, and it's either the second sentence immediately follows the first in raw text, or it's a random one. And the model has to solve this classification problem, that is it truly the next sentence or not? So in this example, you have 1 sentence about deep learning, and then you have another sentence about being allergic to peaches, and so this would be false, that these truly didn't follow each other in natural text. And so both of these tasks can be trained with just large amounts of unlabeled data. And so in the Bert paper, they train it on Wikipedia as well as a corpus of books. And so here's a diagram of the basic recipe. So on the input, at the pre-training time, you start with this special classifier token, and that's just a special symbol that you use to start all your examples. And then you have token by token of the words in the first sentence, where some proportion of them are masked out. And then you have this special separator token that shows the boundary between the first sentence and the sentence seconds, and then token by token of the second sentence. And then you have all of your layers of the transformer in between. And then on the output, you have these 2 different output tasks. So for this special classifier token, which because everything is has self-attention, it could have freely looked absolutely anywhere it wanted. It makes this classification decision, is it the next sentence or not? And then at every position where it was masked out, we predict what word should be. So that's at pre-training time. And then we just completely import this network wholesale to our task of interest. And then when we're training this task, we might slightly modify both the input and the output to fit our task. So if we're doing a question answering task, we would, at the input level, we'd still keep this classifier token, but instead of having a masked first sentence, we would just have a question. And then we'd still have the separator token, and then instead of sentence B, we would put in the paragraph where we're going to look for our answer. And then on the output side, rather than doing the mass prediction task for the next sentence, we're going to classify, well, where is the start of my answer and where's the end of my answer? And you can do similar things for all different styles of tasks. So we would take this same pre-trained model and use it to initialize for name identity recognition or natural language inference or whatever other task you care about. And so this is done very well across tens of tasks. There's a lot of results in the paper. I'm just showing you 2. So one task that this is really good at is the task of common sense reasoning. So these are multiple choice questions where you're given sort of a first sentence of a story and you're asked what would likely come next. So on stage, a woman takes a seat at a piano, and then she sits on a bench as her sister plays with the doll, or does she nervously set her fingers on the keys? And so humans are about 85% of these, and prior state-of-the-art systems were really bad at this. So the best model that didn't use any special language modeling pre-training was 52% accurate. An Elmo model from the prior year that does this pre-trained language modeling but only looks separately to the left and separately to the right got up to 59. And the large version of Bert could get 86. So this is actually better than the humans. And then for the question answering, this is this squad task I told you about. So you're given a question like how far is Jacksonville from Miami, and then a passage, and then you have to give the span that answers the question. So 340 miles. And so here, this is the first time we passed human performance on this data set. And so one question you might ask is, why is this working so well? Which part of the model matters? And so in the paper, they have some ablations. They do ablations for a number of tasks. I'm just going to show you one of them to sort of give you a flavor. So this is for the task of given 2 sentences, are they paraphrases of each other or not? And so, sorry. if I start with the base version of Bert, and so this uses a transformer, it's 12 layers deep. At each layer, it has these 12 attention heads. That gets 86.7. If you remove the next sentence prediction task, you go down to 86.5. So this task actually didn't matter very much. It mattered more for the question answering tasks. So there's some tasks that matters and some tasks it's not very relevant for. Now, if you replace this bidirectional training with left to right, and you only let your self-attention go back to the left, then your accuracy drops drastically. So then it goes down to 77. So you're really, really hurt by not having the bidirectionality. That's where most of the modeling power comes from. And then something you might try to do is say, well, I have these self-attention can only go left to right, but what if I put a bidirectional LSTM on top? Does that help? And the answer is no, that doesn't do any better. Really, you need the bidirectionality to get this to work. And then the other interesting thing is they show experiments with two different sizes of Bert. So Bert base has 12 layers, Bert large has 24 layers, and bigger does seem to be better for pretty much all the tasks we've tried. And this is somewhat surprising because this is true even with really small data sets. So I think we generally knew that, if you have lots and lots of data, like in speech recognition, then bigger models are better. But this supervised task only has 3,000 examples. And yet even with 3,000 examples, it does much better with the 24-layer model than the 12-layer model. So I think that's one nice thing about pre-training is that it tends actually not to overfit even with these much bigger models. And we have some, I should have added this to the speaker references, but we have some work that'll be at iClear 2019 kind of showing what does Bert learn across different tasks. And actually for tasks like co-reference, the large version is much better, thank you, than the base version. Okay, so one question you might ask is, do I need full Bert models for all my tasks? So I just told you there are 24 layers. And I told you you retrain all of the parameters for each task. So if you're in a production environment where you have 10 tasks you care about, do you need 10 different copies of these hundreds of millions of parameters? And so you don't. So we have a paper coming out of Google AI that shows what you can do is you can have these adapter networks. You can freeze most of Bert and then insert these little adapter networks that you fine-tune only those pieces, and that allows you to have much fewer parameters that are changing across tasks while still maintaining the same accuracy. So the chart on the right shows the number of trainable parameters. The y-axis shows the change in accuracy. So ideally you have 0, you have the same accuracy. And if you just do layer-wise fine-tuning, so you say, okay, I'm only gonna fine-tune the top 20 layers or only the top 15 layers, then your accuracy starts dropping. But if you instead do these adapter networks, then you can actually get away with training only 100th of your parameters with pretty much the same accuracy. So you should try it out if you haven't already. So we've open sourced the code as well as these pre-trained models. For both English, we have these 2 different sizes. We've also released a model for Chinese and a multilingual model that covers 102 languages from Wikipedia. And the other thing you can try is it works really well with TPUs. So this is an architecture that makes them much more efficient. So you can try them out with Google Cloud. I put it in a link here and in the speaker resources. And there's an interactive Colab notebook that kind of walks you through how to use it. So you can change individual pieces and then press play and see how it works. And there are free credits for getting started. Okay, so I'm now going to switch gears and talk to you about some challenges that even pre-training doesn't completely solve. So this is when you have mismatches between your training and what you actually see at test time. And I'm going to do 2 case studies. One is mixed language text, and the second is identifying commands. Okay, so having more than one language in your input is something that happens surprisingly frequently in sort of data we see in the wild, but almost never in most of our training sets for most of our tasks. So here are screenshots from Google Translate. I have this input that's a mixture of French and Arabic. And if I say, okay, it's French, please translate it to English, doesn't change anything, just drop some of the words. If I instead tell, okay, it's Arabic, please translate it to English, just passes it through without changing anything. But if I instead broke it up and I gave it just the first piece, and I said, this is all French, then it does perfectly fine, and it translated as things are going well. And if I give it just the second half, and I say, this is truly all Arabic, then it'll translate as I'm fine and you. So it could have done this if not for having gotten confused by the mixed language text. So something that's really useful is to be able to tell our downstream models what language each particular word is written in. And so we trained models to do this. So we have neural networks that at each position can predict the language, but then we run into another problem. So because words are short and out of context, you might get widely different predictions for each position. So if we just ask our model what's the most likely word at each position, it would have predicted, oh, the first word is Vietnamese, and then the second one is French, and then the third one is Arabic and Latin script, and then the fourth one is Polish, and the fifth one is Italian. And it's really unlikely that a human speaker would have used 5 different languages across 5 words. And so what we do is while we score each independently, we then have a dynamic program at decoding time where we say, well, let's say that the speaker is only using at most 2 languages. What's the best path through this lattice that uses at most 2 languages? So, or you can also do 3, but two covers the vast majority of examples and 3 covers the rest. And so if I do this example, then really there's only 2 possibilities. It's either all English and Arabic and Latin script or all French and Arabic and Latin script. So then I really just need to compare this blue path through the lattice with the green path. And then if I sum them up, the green path is best. So I can predict that, okay, it starts off French, and then it switches to Arabic for the rest of the sentence. And so this model does quite well. The model on the right is this work that we published at EM&LP last year, and the other 2 are prior models, and are averaged across a variety of data sets. We can get in the 90s. Prior work was in the 50s or 70s. And you might think, well, are we using a much more expensive model? The answer is no. So this is actually also 1,000 times faster than the prior work. So the prior work was all based on recurrent neural networks, whereas we just have independent feed-forward neural networks that we then combine with the dynamic program afterwards, but that only needs the final scores. It doesn't need the full neural network parameters. And so this is really useful pre-processing across a variety of tasks. So especially we tend to combine it with script correction, and that's really effective. So before, I might have had this query, and if I put it into Google Translate, it says, what is your favorite brunch? So even if you don't speak Hindi, you can say that's probably not right. But if we instead do language identification, even though we make a little bit of a mistake, and then we correct the script, so everywhere we say this looks like Hindi and Latin script, can we convert it to Hindi and Devanagari script? Then this looks like something more like what our models expect. And so if we put this pre-processed input in, then you get what is your favorite Britney song. So our models work better. All right, I'll then move on to our second case study for identifying commands. Okay, so if you want to identify commands, a part of speech tagger is really helpful. If I say, play that song or set an alarm, then knowing that the first word is a verb is really useful for saying what is a command or not. Now, unfortunately, noun-verb ambiguity, especially in the cases of commands, is something that standard part of speech taggers can be really bad at. And this can have a lot of implications also for text-to-speech. So if I have this word lives, then if it's a noun, that's all the information I need to know how to pronounce it. If I say a cat has 9 lives, I pronounce it like lives. Whereas if instead that word is a verb, then I'm going to pronounce it like lives, like she lives in New York City. And so taggers getting this wrong could cause you to pronounce it wrong in your text-to-speech system. And all earlier taggers get examples like the ones on the slides correct. So if I say mark which area you want to distress, every single prior tagger would say, oh, that's a capitalized mark, I know that's a name, and it wouldn't mark it as a verb. And so we created a challenge set plus some methods to address this issue. So you can both evaluate with our data, as well as we created a training set you can use at training time as well. So the results on the left are on the Wall Street Journal Penn Tree Bank, which is the most commonly used data set for evaluating part-of-speech tagging. And here's a number of different taggers. The one all the way on the left is the Stanford part-of-speech tagger, which came out over 15 years ago. The ones in the middle are state-of-the-art taggers from the past couple of years, optionally including contextual embeddings. And if you look on the standard data set, you might say, why would you bother to research this problem? In 15 years, absolutely everything is 97.x accurate. Doesn't matter what you do. These are all the same. But if you measure on our data set, actually there are quite a bit of differences. We actually have been making improvements. We just weren't able to measure them. And the same set of taggers ranges from in the 50s to in the high 80s. And BERT-based models can get in the 90s. And so zooming in on the right part of the chart, we look at accuracy on our task. This was a state-of-the-art tagger, also from my group, that won the shared task on universal dependencies last year for tagging, and it was only 74% accurate. And if we then enhance it with Elmo contextual embedding, so another precursor to BERT, then it improves quite a bit, improves 8% absolute. And this was notable because actually on the prior data sets, it hadn't shown any impact on syntax, even though a lot of people had the intuition that these pre-trained language models should have been capturing a lot about syntax. So if you have a different representation and you want to probe it for what is it learning about syntax, you might want to try our data set as well. And then using our training set, you can get even better. And then if you combine both, you do better than either one of them individually. That's also somewhat interesting that you can either have billions of unlabeled examples, or you can have tens of thousands of very targeted labeled examples, and they both add different things. And this carries over to downstream applications. So this is now not the tagging task, but a pronunciation task. So you're given a word in context, like this lives or lives, and you're asked, well, how should I pronounce it? And so on the left was the prior best machine learned model for pronunciation. And then the ones on the right are just how well do you do if the only information you use is what is the word and what is the part of speech tag. So you could probably do better doing more things, but we can give 20% relative improvements with these better taggers. And so, well, I've told you about one specific data set. This is part of a theme of our work that we've been trying to release challenge sets that have naturally occurring examples that you see in the wild to try and help the academic research community see the kind of challenges we face. So we've publicly released this data set of noun-verb ambiguity. So the examples look like this, where there's one word labeled, and then you have a context, and it's labeled as noun or verb. We have another one we've released for co-reference resolution. So there's a pronoun with two different distractor entities, and you have to say which one does it co-refer with or neither. And one special thing about this data set is it's gender balanced. So a lot of existing data sets have the vast majority of examples are masculine, and so then systems tend to be better at predicting the masculine examples because that's what it's seen more in training time. And so this data set contains a large number of feminine examples as well. And there's also a Kaggle task for this. So if you're interested, you can compete. We're offering $25,000 in prize money for the best system. And then the third data set we've released recently is the data set for natural questions. So one issue with a lot of question answering data sets is they come from giving annotators a passage and then asking them to come up with a question. And this leads to questions that might not be natural or might tend to stay really, really close to the passage. And so we created a data set where all of the questions are real questions that people ask. Lots of people have asked these questions. And then after the questions are fixed, we then ask annotators to find, can you find the answer to these questions? So you can see an example of when are hops added to the brewing process. And our data set contains both the actual answer, so like the boiling process is the answer, as well as what is the larger paragraph that leads you to know this answer. So we have there's a couple 100,000 of examples here. I recommend you use it. And we have a leaderboard up if you want to compete. Okay, so in conclusion, try out Bert for your tasks if you haven't already. I think it's an exciting time for NLP that you don't have to create these very complicated custom architectures. You can really get started by just starting with a model and then really thinking about, well, what do I want my input to be? What do I want my output to be? Do I want to try pre-training on my custom data? Do I want to adjust the objective? But I think it's much easier to get started than it used to be. And then the second lesson is be aware of what linguistic phenomena are in your data. So if you're seeing things like commands and you've trained completely on Newswire, you might want to know that. If you have a lot of mixed language text and all of your training data is completely monolingual, that's a good thing to be aware of. And if you're working on models for question answering or part speech tagging or co-reference, then try your models out on our naturally occurring challenge sets. And I now have a few minutes for questions, and I'll also be around at lunch and the breaks. Thanks.
Hi, thank you for that. My name is Paul, and that was really interesting. So we're actually comparing Bert to some of the competitors like Laser and GPT-2, and I think Microsoft just released one or something like that. So I just wanted to know if you wanted to badmouth your competition or at least give some advice on how to compare the models other than just looking at benchmarks.
No, I don't want to badmouth any competitors. So one thing, there's a interesting overview article that Noah Smith from the University of Washington just put out on Archive that I recommend. That I forget exactly which set of models he compares. I think it's definitely Bert and Elmo, and I think a few others. And one thing he looks at is, so there's a couple different styles of using these models. There's the pre-training and fine-tuning approach that I mostly talked about. But then there's also the approach of using it to derive features and then using it in your fixed in your model. And so some models are better in the fine-tuning approach, some models are better in the feature approach, and depending on your task, you might prefer, or on your other constraints, you might prefer one or the other. So I would recommend that resource to take a look at some of the comparisons.
Hi, I'm Mbika. I was wondering, how are you guys masking? Are you guys doing this manually, or are you using another type of network to do that?
Yeah, that's a great question. No, it's not manual. It's just random. So what it is you take all of the tokens, and then with each token, I think it's with 15% probability you mask it, and 85% you don't mask it. And then there's actually some details that I skimmed over a little bit. You can read the paper. Is that the majority of the time we replace it with a masked token. Some small proportion of the time we also keep the original word to try and have it also learn what should go there. And some proportion of the time we replace it with a random word so it also doesn't just learn to copy.
So for pre-training with a BERT model, the masking and the next sentence prediction is at the same time. Mm-hmm. And then my second question is, what tasks do you know BERT does not perform well at? So just versus a hammer, is it's probably not a hammer, but so what does it not do well at?
Great questions. So for your first question, yes, you do the masking and the next sentence prediction at the same time. So it's just you predict them at different positions. So for the next sentence prediction, you use the output of this special classifier token, and the masked prediction you do at the individual token that was masked out. For your second question of what does it not do well at, I think there have been a bunch of data sets coming out that are actually kind of adversarially created to match what does it not do well at. So there's a couple new data sets out of the Allen Institute, AI2, that are created with what Bert can't do. So one of them is focused on quantitative reasoning. One of them is focused on visual common sense. So I think we'll see more and more of these of like focusing on sort of the weaknesses.